Welcome back to algo.monster. Today, let's solve another coding interview question. Welcome to our LeetCode problem-solving session. Today, we'll be tackling problem number 2818. Apply operations to maximize score. This is classified as a hard problem. Let's understand what this problem is asking. We're given an array of positive integers called nums and an integer k. Our goal is to maximize a score by performing up to k operations. We need to return the maximum possible score modulo 10 to the power of 9 plus 7. This problem involves concepts from array manipulation, mathematics, and greedy algorithms. Let's break down how each operation works. We start with a score of 1. For each operation, we follow these steps. First, we select a non-empty subarray from our nums array that we haven't chosen before. For example, if nums is 2, 3, 6, 5, 4, we might choose the subarray 3, 6, 5. Second, we need to find the element with the highest prime score in this subarray. The prime score is the count of distinct prime factors of a number. For example, 3 has a prime score of 1 because it has only one prime factor, 3 itself. 6 has a prime score of 2 because it has two distinct prime factors, 2 and 3. 5 has a prime score of 1 because it has only one prime factor, 5 itself. Third, if multiple elements have the same highest prime score, we choose the one with the smallest index. In our example, both 3 and 5 have a prime score of 1, but 3 comes first, so we would choose 3. Finally, we multiply our current score by the selected element. If we had chosen 6 with a prime score of 2, our new score would be 1 times 6 equals 6. A key part of this problem is understanding the concept of prime score. The prime score of a number is simply the count of its distinct prime factors. Let's look at some examples. The number 12 can be broken down as 2 squared times 3. It has two distinct prime factors, 2 and 3. So its prime score is 2. The number 14 can be expressed as 2 times 7. It has two distinct prime factors, 2 and 7. Its prime score is also 2. The number 11 is a prime number, so its only prime factor is itself. Its prime score is 1. The number 30 can be factored as 2 times 3 times 5. It has 3 distinct prime factors, giving it a prime score of 3. The number 16 is 2 to the 4th power, which has only one distinct prime factor, 2, so its prime score is 1. And finally, the number 1 has no prime factors, so its prime score is 0. When performing operations, we'll need to calculate these prime scores to determine which element to select from our subarray. Now let's clarify the overall goal and constraints of this problem. We start with a score of 1, and we can perform up to k operations. In each operation, we select a subarray, find the element with the highest prime score, and multiply our current score by that element. Our goal is to maximize the final score after these operations. The operations build on each other. We start with 1, multiply by our first chosen element to get score 1, then multiply by our second chosen element to get score 2, and so on, until we reach our final score after k operations. There are two important constraints to remember. First, each subarray can only be selected once. This means we need to strategically choose which subarrays to use. Second, since the score can get very large, we need to return the final score modulo 10 to the power of 9 plus 7. The challenge is figuring out which subarrays to choose and in what order to maximize our final score. Let's work through an example to better understand this problem. We have the array nums, chos 6, 12, 5, and we can perform k as 2 operations. First, we need to determine the prime score of each element. The number 6 equals 2 times 3, giving it two distinct prime factors. Similarly, 12 equals 2 squared times 3, also giving it two distinct prime factors. And 5 is already a prime number, so it has just one distinct prime factor. Our goal is to pick two subarrays that will maximize our final score. Let's try our first approach. For our first operation, we'll pick the entire array, 6, 12, 5. Looking at the prime scores, both 6 and 12 have a score of 2, while 5 has a score of 1. When there's a tie, we pick the element with the smaller index, which is 6. so our score becomes 1 times 6, which equals 6. For our second operation, we'll pick the remaining elements, 12, 5. Here, 12 has the highest prime score of 2. This makes our final score 6 times 12, which equals 72. But we need to ask ourselves, is this the optimal strategy? Let's explore other possibilities. Let's try a different approach. For our first operation, we'll pick just the subarray, 12. Since there's only one element, it has the highest prime score. Our score becomes 1 times 12, which equals 12. For our second operation, we'll pick the subarray 6, 5. Here, 6 has the highest prime score of 2. This makes our final score 12 times 6, which equals 72. Interestingly, we end up with the same final score of 72 as our first attempt. But is this the best we can do? Let's try one more approach. Here's the optimal strategy. For our first operation, we pick the subarray, 12. As we saw before, this gives us a score of 1 times 12, which equals 12. But here's the key insight. We can reuse the elements with the highest prime score in different subarrays. For our second operation, we can pick the subarray 12, 5 again. The highest prime score element is still 12, making our final score 12 times 12, which equals 144. This is much better than our previous attempts that gave us only 72. The maximum possible score for this example is 144, which we achieve by selecting the element with the highest value multiple times. This demonstrates an important strategy for this problem. Prioritize the highest value elements when selecting subarrays. To maximize the score, our approach revolves around two key insights. First, since our score is a product of selected elements, we should prioritize larger values. This makes intuitive sense. Multiplying by larger numbers yields larger results. Second, we need to determine how many times each element can contribute to our score. An element can only be selected if it has the highest prime score in a subarray. This leads to a critical question. For each element, in how many unique subarrays does it have the highest prime score? To answer this question, we need to find boundary positions for each element. The left boundary is the leftmost position where no element with a higher prime score exists. The right boundary is the rightmost position where no element with a higher or equal prime score exists. With these boundaries, let's call them L and R, we can calculate the total number of valid subarrays for each element as IL times Ri. This formula gives us the count of subarrays where our element has the highest prime score. Our optimal strategy becomes clear. Calculate boundaries for each element using monotonic stacks. Sort elements by their values in descending order. Greedily select elements with highest values first until we've used all k operations. For each selected element, we contribute value raised to the power of its count to our score. This greedy approach ensures we're always selecting the most valuable elements first, while respecting the prime score constraints of the problem. Let's walk through the solution with the example. Nums equals 6, 12, 5, and k equals 2. In step 1, we calculate the prime scores for each number. For 6 at index 0, the prime factors are 2 and 3, giving it a prime score of 2. For 12 at index 1, the prime factors are also 2 and 3, resulting in a prime score of 2. For 5 at index 2, the only prime factor is 5, giving it a prime score of 1. We then create a data structure containing tuples of index, prime score, and value. 0, 1, 5, 2, 6, 1, 2, 12, 2, 1, 5. In step 2, we find the left boundaries using monotonic stacks. For each position, we need to find the previous element with a prime score greater than or equal to the current element. For index 0, there are no elements to the left, so the boundary is -1. For index 1, the element at index 0 has the same prime score of 2, so the boundary is 244, 0. For index 2, the element at index 1 has a higher prime score 2 compared to 1, so the boundary is 241. This gives us left boundaries of -1, 0, 1. In step 3, we find the right boundaries for each element. For right boundaries, we look for the next element with a prime score greater than the current element. In our example, since there are no elements with higher scores to the right for any position, all right boundaries are set to 3, which is the length of the array, so we have right equals 3, 3, 3. In step 4, we first sort by value in descending order, giving us 1, 2, 12, 0, 2, 6, 2, 1, 5. Then we process the element with the highest value, which is at index 1 with value 12. Using the boundaries we found earlier, left 1 equals 0 and right 1 equals 0, 3, we calculate the count as 1 minus 0 times 3 minus 1 equals 1 times 2 equals 2. Since k equals 2, we can use all operations available. The score for this element is 1 times 12 squared equals 144. After using all operations, so we can't process more elements. Therefore, the final score is 144.
Before we get into the code, if you want to practice yourself, check out our new interactive practice tool on algo.monster, where you can practice coding problems like an actual interview.
In our solution, we first need a helper function to count distinct prime factors. Here we initialize our variables. D starts at 2, the smallest prime number, and we use a set to track unique factors. This function will determine the prime score of each number in our array, which is crucial for our algorithm. Now we're implementing the core logic of our prime factorization function. We use a while loop to find all prime factors less than or equal to the square root of n. For each potential factor, we repeatedly divide n by that factor and add it to our set. In this example with the number 12, we've found that 2 is a prime factor and have divided 12 by 2 twice, resulting in n equals 3. We complete our prime factorization by checking if any remaining value of n is greater than 1. If so, it must also be a prime factor. For our example of counting prime factors in 12, we found factors 2 and 3, giving us a prime score of 2. This prime score concept is key to our solution. Now we begin our main solution by creating a data structure that holds all the information we need. For each number in the array, we store a tuple containing its original index, its prime score calculated using our helper function, and its original value. This prepares us for the next step of finding boundaries. In our example with input array 2, 12, 7, 5, we calculate the prime scores. 2 has 1 prime factor, 12 has 2 prime factors, 2 and 3. 7 has 1 prime factor, and 5 has 1 prime factor. This gives us items such as 0, 1, 2, 1, 2, 12, 2, 1, 7, 3, 1, 5. We also initialize arrays for left and right boundaries, which we'll use in the next steps to efficiently count subarrays. In this step, we find the left boundary for each element using a monotonic stack. The left boundary represents the previous position with a higher or equal prime score. We process elements from left to right, maintaining a stack of tuples with prime scores and indices. Looking at our example, for the first element, 0, 1, 2, there are no previous elements, so its left boundary remains -1. For the second element, 1, 2, 12, we pop the previous element from the stack, since 1 is less than 2, leaving an empty stack, so its left boundary is also -1. For 2, 1, 7, since its prime score is less than the stack top's score, we update left 2 equals 1, indicating position 1 is its left boundary. Similarly, for 3, 1, 5, we set left 3 equals 2. Our final left boundary is array -1, -1, 1, 1, 2. Similarly, we find the right boundary for each element by processing the array from right to left. The right boundary represents the next position with a higher prime score. We start from the last element, 3, 1, 5, and work backward. For element 1, 2, 12, all elements to its right have lower prime scores, so its right boundary is 4, the array length. For element 0, 1, 2, the right boundary is 1 because element 1, 2, 12 has a higher prime score. After processing, we get right boundaries 1, 4, 4, 4. Together with the left boundaries, this allows us to count how many subarrays have each element as their prime score champion. For our greedy approach, we sort the elements by their values in descending order. This is crucial because we want to prioritize higher values in our operations to maximize the final score. The sorted order ensures we apply operations to the most valuable elements first, as long as we stay within our k operation limit. In our example, the sorted order becomes 1, 2, 12, 2, 1, 7, 3, 1, 5, 0, 1, 2. Placing the element with value 12 at the front, followed by 7, 5, and 2. This ordering is key to our greedy strategy of maximizing the score. Now we calculate the maximum possible score by iterating through our sorted elements. For each element, we determine how many subarrays have this element as their prime score champion using the formula I, left, right young I. In our example with k equals 3, for the element with value 12, the left boundary is -1 and the right boundary is 4, giving us open parenthesis 1 minus -1, close parenthesis, times open parenthesis 4 minus 1, close parenthesis, equals 2 times 3 equals 6 subarrays. Since we only have k equals 3 operations, we can only use 3 of them, resulting in a final score of 12 cubed equals 1,728. We've used all our operations, so we break from the loop and return the result. Let's look more closely at how we count subarrays. The formula count equals I minus left I times right I minus. I gives us the total number of subarrays where an element has the highest prime score. For element 12 at position, I equals 1, with left 1 equals -1, and right 1 equals 4, we have 2 options for the left endpoint, positions 0 and 1, and 3 options for the right endpoint, positions 1, 2, and 3, 3. Multiplying these options gives us 2 times 3 equals 6 total subarrays, 2, 12, 12, 7, 2, 12, 2, 12, 7, and 12, 7, 5. In each of these subarrays, 12 has the highest prime score, so each contributes value 12 to our final score calculation. Let's analyze the time complexity of our solution. First, finding the prime factors for each element takes O(n) times the square root of m time, where n is the number of elements and m is the maximum element value. Building the monotonic stacks to determine the boundaries requires O(n) time. Sorting the elements by their prime scores takes O of n log n time. Finally, calculating the contribution of each element to the final score takes O of n time. When we combine these operations, our overall time complexity is O of n log n plus n times the square root of m. Now let's look at the space complexity of our solution. We need to store several data structures for our algorithm. First, we have arrays for storing the original elements, which takes O(n) space. Next, we need arrays for storing the boundaries determined by our monotonic stacks, which also takes O(n) space. Additionally, we use stacks for our monotonic stack implementation, which in the worst case might store all n elements. When we combine these space requirements, the overall space complexity of our solution is O(n). This means our solution scales linearly with the input size in terms of memory usage, making it very efficient for large inputs.